We are going to discuss one of the most transformative, yet often misunderstood concepts in modern urban planning: digital twins. Our title is Key Concepts and Frameworks. This means we are not just here to look at visually impressive 3D city models. Instead, we will explore the theoretical foundations, taxonomies, and management frameworks that shift planning from static maps to dynamic, living simulations. First, we will start with conceptual definitions, because not every 3D model is a twin. Next, we will look at classification systems, taxonomy, to clear up the confusion in the industry. Then, we will examine the system architecture and resilience models that make these systems work. Finally, we will move beyond the technology to discuss the socio-technical governance and analyze real-world case studies from Zagreb and Cambridge. By the end of this session, we aim to achieve 4 key outcomes. First, you will be able to define the distinct difference between a digital twin and traditional GIS or static models. Second, you will understand the theoretical architecture, how data flows from sensors to the model. Third, you will explore how this technology offers specific conceptual models for ecological and resilient planning, particularly in disaster management. And finally, you will be able to analyze the essential classification systems, like DTUCS, which are necessary for effective implementation. In this slide, we clarify the ontological shift. Often, simple 3D models are mistaken for digital twins. As illustrated in the diagram, 1. If the data exchange is manual, it is just a digital model. 2. If the data flows only one way, monitoring, it is a digital shadow. 3. A true digital twin requires a bidirectional loop. The virtual system doesn't just watch the city. It sends information back to optimize it, whether through automatic traffic signals or informing policy decisions. As referenced in the Zagreb case study by Cisco et al., having a detailed 3D map is only the starting point, not the destination. Please look at the arrows in this diagram, as they define our concepts. On the left, the digital model has dashed arrows. This means data entry is manual. If a building changes in the city, an operator must manually update the file. This is where most 3D city models are today. In the middle, the digital shadow has a solid arrow going up. Sensors automatically update the model, but the model cannot send commands back. On the right, the true digital twin. Notice the complete loop of solid arrows. The system not only monitors the city but can send automated responses back to the physical world. This bidirectional flow is the core definition of a digital twin. Asterisk. Moving on from definitions, we face a major hurdle: ambiguity. As highlighted by Al-Sarawi et al., 2021, the planning industry suffers from a lack of standardized terminology. Right now, anyone with a 3D model claims to have a digital twin. This confusion creates data silos and prevents effective collaboration. This brings us to the concept of taxonomy. Just as biology classifies living organisms to understand them, we need a classification system for digital twins, called DTUCS. Without this common language, taxonomy, effective knowledge transfer between a city planner and a software engineer is impossible. We need to define the use before we build the tool. Now, let's look at how we actually construct this common language using the DTUCS framework proposed by Al-Sarawi. This slide covers the first 2 essential layers of the system. First, we have Layer 1, standardized to publish. In urban planning, we deal with a massive problem called data heterogeneity. We have BIM models from architects, GIS maps from surveyors, and IoT data from traffic sensors. They all speak different digital languages. This layer is about interoperability. Before we can build a twin, we must convert these raw, messy datasets into standardized formats, like IFC or CityGML. Without this step, the twin is just a disconnected collection of files, not a system. Then, we move to Layer 2, detail to prove. This is about efficiency. A common mistake in digital twinning is trying to model everything at maximum quality. This layer introduces the concept of fitness for purpose. We must define the correct level of detail, LOD. For example, if we are simulating citywide traffic flow, we do not need to model the door handles on every building. That would be data waste. This layer ensures we model only what is necessary to answer the specific planning question, keeping the system light and responsive. Moving on to slide 7, we reach the final and perhaps most critical layer of the DTUCS framework: classify to reach. A digital twin is a massive database, but it serves multiple masters with very different needs, from city planners and engineers to politicians and ordinary citizens. The biggest risk here is information overload. If we show a mayor the same raw technical data we show a structural engineer, we will confuse them, not help them. This layer acts as a translator. It filters and contextualizes the data based on who is looking at it. For a city planner, the system might display high-level zoning densities and heat maps. For a citizen, it might show realistic 3D visualization of a new park to gauge public opinion. For an engineer, it reveals the underground utility pipes. Ultimately, Al-Sarawi argues that a digital twin is not just a calculation tool, it is a communication tool. This layer ensures the right information reaches the right person in the right format, which is essential for effective governance. Now that we understand the classification, let's look under the hood. How does a digital twin actually work? Based on the framework by Lee et al., 2025, we can break the architecture down into 3 logical layers. First, at the bottom, we have the physical layer. Think of this as the senses of the city. It includes everything that collects data: traffic sensors under the asphalt, drones flying overhead, or even smartphones used by citizens. This is where data acquisition happens. Second, the network layer. This is the bridge. Gathering data is useless if we can't move it. This layer uses technologies like 5G and edge computing to transmit massive amounts of data from the street to the server instantly and securely. Finally, the virtual layer. This is where the magic happens. The raw data arrives here and is combined with the 3D geometry. This is where algorithms clean the data and run simulations. The key takeaway here: a digital twin is not a single software. It is a stack of technologies working in a continuous loop. We have discussed the architecture, but there is a missing link: intelligence. In slide 9, we address the modeling approach. The most critical concept here is the distinction between geometry and semantics. A standard 3D model is purely geometric. It tells the computer, here is a box, located at these coordinates. But a digital twin must be semantic. It needs to tell the computer, this box is a hospital. It has 200 beds, consumes this much energy, and was built in 1990. This difference is vital. If I ask the system, show me all buildings at risk of collapse, a geometric model cannot answer. A semantic model can, because it knows the age and material of every building. We also use ontologies, which are logic rules connecting these objects, like understanding that a road connects to a bridge. This semantic richness allows us to merge broad GIS maps with detailed BIM models into one unified system. Up to this point, we focused on urban buildings. But as Lee et al., 2025, demonstrate, one of the most vital applications of digital twins is resilience and ecological planning. Here, the digital twin is not just a map, it is a safety mechanism. We can conceptually divide this into a 3-phase life cycle. First is the pre-disaster phase. This is about prediction. We don't wait for a fire or flood to happen. We simulate it in the twin. We ask, if the wind blows from the north, which houses are at risk? This allows planners to create better safety zones before a crisis occurs. Second is the during disaster phase. This is about situational awareness. When a disaster strikes, the twin fuses real-time data from drones and sensors to show exactly where the danger is right now, helping emergency teams navigate. Third is the post-disaster phase. This is about recovery. The twin helps calculate damage and plan the fastest route to restoration. In summary, this model shifts planning from being reactive, fixing things after they break, to being proactive, anticipating risks. Highlights the most powerful capability of a digital twin: time travel. Traditional planning is often reactive. We look at past data, see a traffic jam or a heat island, and try to fix it. We are always chasing the problem. Digital twin technology shifts us to predictive planning. Instead of looking backward, we look forward using what-if scenarios. Because the twin is a physics-based simulation, we can perform virtual experiments that would be impossible or dangerous in the real world. For example, consider ecological planning. Before laying a single brick, we can simulate. If we build a high-rise here, will it block the wind corridor? Will it create a heat island effect? By answering these questions in the virtual world, we prevent environmental damage in the physical world. This shifts the planner's role from a problem solver to a future optimizer. We have discussed sensors, architecture, and simulations. But as Wan et al. 2019 argue in their Cambridge case study, technology is actually the easy part. Slide 12 introduces the most critical concept for planners: the digital twin as a socio-technical system. The biggest mistake cities make is treating the twin as a software product, something you just buy and install. But a city is not a machine, it is a society. Therefore, the twin must integrate three things. 1. Technology, the hardware and code. 2. Governance, the laws and rules about who owns the data. 3. People, the citizens and planners who actually use it. Wan et al. Propose a middle-out approach. You cannot just force a system from the top down, nor can you wait for it to happen from the bottom up. You need a collaborative framework where policy meets innovation. Without this social integration, the most advanced technology will fail to produce value. The Gemini principles, which are considered the global gold standard for digital twin governance. Developed in the UK, they provide the ethical framework. They are divided into 3 pillars. 1. Purpose. Above all, the twin must serve the public good. It is not just about efficiency or profit, it must benefit the environment and society. 2. Trust. If citizens do not trust the system with their data, the project will fail. Therefore, the twin must be secure and transparent. 3. Function. The system must function effectively through federation. This means avoiding monopolies and allowing different systems to talk to each other. For us as planners, these principles are our moral compass. They ensure we build smart cities that are ethical, not just technological. This slide answers a critical question. How do we build a twin for a whole city? Do we put everything into one giant superfile? The answer is number. That is the monolith myth. Such a model would be too heavy, too expensive, and impossible to update. Instead, we use the federated approach, as championed by the UK's National Digital Twin Programme. Imagine the city as a team of specialists. The water department has a water twin. The transport department has a traffic twin. The energy company has a grid twin. In a federated system, these twins remain separate but are connected. They talk to each other. Example: if a water pipe bursts, water twin, it automatically alerts the traffic signals to close the road, traffic twin. This approach is scalable and secure. It allows the ecosystem to grow organically, just like the internet, rather than trying to build a perfect world from day one. A common pitfall in planning is expecting a matrix-style, autonomous city on day one. In reality, the digital twin is an evolutionary process. We use maturity models to track this progress. It starts at level 0, just a static 3D map. Level 1 is descriptive. We add sensors. Now we can see traffic jams in real time. Level 3 is where the planner truly benefits. This is the predictive stage. We can ask what-if questions. The ultimate goal is level 4 autonomous, where the traffic lights change themselves to clear a jam without anyone pushing a button. Understanding this spectrum is vital for managing expectations. Planners must realize that building the geometry is just the starting line, not the finish line. Before we move to the case studies, we must address the elephant in the room. If digital twins are so powerful, why doesn't every city have one? Slide 16 highlights the 3 major barriers to adoption. 1. Data silos. This is the biggest enemy. In many cities, departments do not share data. If the water department keeps its data locked away from the transport department, you cannot build a federated twin. 2. Interoperability. This is the technical struggle. Getting a building model, BIM, to sit perfectly inside a city map, GIS, is technically very difficult. It's like trying to put a square peg in a round hole. 3. The skill gap. Finally, we have a human problem. Most planners are trained to draw maps and write policies, not to manage real-time IoT sensors. These challenges explain why the maturity levels we just discussed take years to climb. Our first case study is the gold standard for digital twin policy, Cambridge and the UK National Digital Twin Programme, as analysed by Wan et al., 2019. Why is this case important? Because they solved the scale problem. They realized that you cannot build a single digital twin for an entire country, it's too big. Instead, they adopted the federated approach. They decided to build an ecosystem where the transport twin connects to the energy twin, and the London twin connects to the Cambridge twin. Their major contribution was not software, but governance. They created the Information Management Framework, IMF. Think of the IMF as the grammar of the language. It ensures that when a sensor in Cambridge says, high traffic, the server in London understands exactly what that means. This proves our earlier point. Successful digital twins are 20% technology and 80% governance. Our second case study takes us to Zagreb, analyzed by Cisco et al., 2024. While Cambridge showed us the governance side, Zagreb shows us the technical evolution. Zagreb had a problem common to many cities. They had a beautiful 3D model of the city, LOD 2, but it was dumb. It was just pretty geometry with no intelligence. To bridge the gap to a digital twin, they didn't try to wire up the whole city with sensors overnight. Instead, they focused on a specific problem: solar energy. They integrated algorithms to calculate the solar potential of every rooftop in the city. Suddenly, the static model became a dynamic planning tool. A planner could now click on a roof and see, is this a good place for solar panels? The lesson here is vital. Digital twins are built iteratively. You start with a map, add an analytical layer, like solar, and step by step, you climb the maturity ladder. To conclude, let's summarize the key takeaways from our research on concepts and frameworks. 1. Process over product. We learned that a digital twin is not a static file you save on a computer. It is a dynamic process defined by the loop of data between the real and virtual worlds. 2. Language matters. We cannot build what we cannot define. The DTUCS taxonomy is essential for planners and engineers to speak the same language. 3. Predictive power. The real power of the twin is not looking at what happened yesterday, but simulating what might happen tomorrow, especially for resilience and ecological planning.